upper division courses that involve some of those topics. So I'm just going to jot them up on the board here for you. Several of you indicated you were interested in aeronautics and astronautics, and central force motion is a whole field of engineering. Orbital mechanics is the field in aerospace engineering, orbital mechanics. And you can just imagine the complexity of trying to rendezvous. Imagine trying to get a space shuttle or some other device to rendezvous with some other orbiting body. Imagine trying to insert something into, back in the Apollo days when I was in college, of them sending a manned space capsule into high orbit around the Earth and then kicking it off with the right amount of thrust so that it can essentially glide and intersect an orbit on the moon. Then decelerate and go into orbit around the moon, and then send off another small capsule, a landing module, to actually go down and land on the surface. Then come back up, rendezvous with that orbiting body, the recovery vehicle, and then have enough propulsion to be able to fire itself and then glide back to where you come back into the influence of the Earth's gravitational field, get pulled back into the Earth's, accelerate back into the Earth's gravitational field, and come in at just the right angle and decelerate so that you can re-enter the atmosphere and land safely. Orbital mechanics. So it's fascinating, just a fascinating area of study. Huge amounts of energy, mental energy and physical energy required to put objects up outside our atmosphere or into high atmospheric types of trajectories and not even leave the atmosphere. So anyway, we're not taking time on it because we don't live in the aerospace communities, but central force motion is an important area of study, and it's touched on. Kepler did some of the early work in that long before we could fly, even in the atmosphere. And if you study that material a little bit, orbital mechanics, or at least the orbits of satellites under central force fields follow elliptical paths. And you studied a rectangular coordinate system approach to elliptical motion, but the most powerful one for use for analysis is actually in a polar form, involving eccentricity and that type of thing. So don't neglect that. It's a topic covered in your calculus textbook, and it's also covered here. Another section in this chapter that we don't cover is relative motion, where we look at the energy involved. You have more than one body, and they're moving one relative to another. And now we did a touch on it, I guess, with impact, but that's when they actually come together and then depart again. But we didn't look at it from a relative velocity or relative motion concept. So you can take systems of particles, and you can do analysis there. There's another brief section there that closes this chapter, chapter 3. The next chapter that we skip is chapter 4, and what it's on is kinetics of systems of particles. Like when the holidays come around, we have like the 4th of July and so forth. One simple example is you fire a rocket into the air, and you know it's going to follow a parabolic flight path. Well, that wouldn't be very exciting to just watch 4th of July fireworks go up and do their parabolic flight path. So what they do is they go up and they explode. So once their mass is then fragmented into all kinds of nice little things, particles sent off and doing all kinds of fancy things. But there is a mass center that still follows that parabolic flight path. So there's this, in the explosion or the separation going on here, there's forces that cause these objects to fragment and separate, and they go off doing their own thing under the action of that unbalanced force that broke it apart in the first place, but the mass center of those combined system of particles still follows that flight path. So that's one simple example of that. You can do these problems with F equals ma, and you have to account for the motion of the mass center, and then you also account for the motion of the individual particles that make it up. You can do the energy analysis. You can do F equals ma, you can do work energy, you can do impulse momentum on systems of particles, and actually studying the kinetics of systems of particles. Historically, here at Lane, we've skipped that chapter because if you need that stuff, you've got enough of a grounding in your kinematics of particles and the introduction to single particle and a little bit of impact where you got a couple particles interacting, or where particles are hooked together with cables. You got a strong enough background that if you need this at intermediate or more advanced level dynamics courses, it'll come pretty easy to you. Okay. So that then gets us to chapter 5, where we now move on to something called a rigid body. And I want to put an illustration up here, and if I get time in the next week or so, this is a photo that's in the opening part of chapter 5 of the book. This is inside a transmission. And these gears, these planetary gears, rotate as they stay in this outer shell. And so they form, they perform circular motion as they rotate around this, and then there's another drive mechanism on the inside here. And there's some interesting analysis we can carry out related to that type of a thing. Okay, so let's go ahead and get started on the rigid body kinematics. And we'll start with rotation. If we take a body called a rigid body, and if we would etch a line on that body, and then I etch another line on that body, then any points on this body do not move relative to one. The only way they would move relative to one another is through rotation. There'd be no contraction between 2 points or extension, no shortening or lengthening of any dimensions on that body. Okay. Now, if we would set up an axis somehow, a reference axis, then these etched lines that we've placed on this body, we could measure an angle, theta 1, that line makes with the reference axis, and we could measure similarly the angle that the other line makes. Now what I want to do is check and see what they did in the book on this, just to make sure we do it right. And they called the angle between these two then angle beta. Angle beta. So you can see that theta 2 equals theta 1 plus beta. Now if we start differentiating here, theta 2 dot is going to be equal to theta 1 dot, and theta 2 double dot is going to be equal to theta 1 double dot, since beta is constant. So that's useful. If you're on a single rigid body, then the angular rotational rate, no matter how you reference it, is going to be the same no matter where you are on that body. In the positive sense as shown here, these would be, you could think of these quantities, these velocity, rotational velocity, and acceleration quantities as being out of the board at you by your right-hand rule. By your right-hand rule, coming out of the board at you. Okay. Rigid bodies can have pure translation and the book calls that, I think, probably just translation. They call it rectilinear translation. So that means the rigid body is going to move rectilinearly. So all points are going to move like that. Okay? We can have curvilinear translation, where the body follows a curved path but doesn't change its orientation. Okay. Then we can have fixed axis rotation, and that's where your body is pinned about some spot, and it doesn't even have to be pinned at a particular spot on the body. It could be pinned at some spot off the body, and the body tends to rotate about that. Fixed axis rotation. And then the final is the combination of curvilinear translation and fixed axis rotation. So that's like tossing your dynamics book into the air. It can translate and it can rotate, tumble at the same time. And that'd be the general motion. Question?
It wouldn't be, there isn't another category of general motion in there that would be non-fixed axis rotation, so it'd be moving on an axis that was moving around at some...
That would be the general motion.
Okay, so the movement of the axis is tied in with the translation of the body.
Yeah. And you can see this illustrated in their drawings in the textbook here. Okay. So, just to keep you in familiar territory, you folks were pretty good, I think, with this. ds dt equals v, dv dt equals a, and then eliminating the time parameter there, v dv equals a ds. Started the course out there. If we're in rotation, then this would be analogous to d theta dt is angular speed, omega. d omega dt equals alpha, angular acceleration. Rate of change of angular velocity with respect to time is angular acceleration. Typical units, radians per second squared, radians per second. Eliminating the time parameter right there, we're going to have omega d omega equals alpha d theta. So the mathematics, you got lots of practice early in the course doing this, and you can now handle rotational motion this way. Rotational motion like this. Feeling good? Okay. Let's look at circular motion now. Special case of circular motion. Circular motion. So, let's say I set up an axis from which I'm measuring theta. So we can take this object and say that it's rotated some amount theta. It now happens to be, this point has gone now to this location. And this is under the action of potentially some omega and some alpha. Angular velocity and angular acceleration. But we're in a special case of circular motion. We know that this arc length down here is equal to the radius times theta. We know that the speed the object is carrying at that instant is the time derivative of this. S dot holding r constant, theta dot. So S dot is V is equal to r theta dot equals r omega. Everybody feeling real comfortable? Falling asleep, some of you. Okay. I'm going to move this. So here's our omega, and we have some alpha potentially. Now, the reason I wanted this space over here is because there's also a tangential acceleration, which is S double dot, which is the time derivative of this. R omega dot, which is, omega dot is right here, is alpha. You folks should know this stuff well enough to be able to present it. I'm just doing stuff you've seen many times before, right? Okay. Maybe I'll let one of you teach this stuff next class session. Okay. Okay. Now, there's another piece of acceleration we all know about towards the center of curvature, since we're on a circular path, and that's pointing right back this direction, and that's the thing we typically call our normal acceleration, and that's equal to v squared over r, but v is r omega. Substituting it in there, this is r omega squared. So that little drawing has all of the kinematics for circular motion. All right? Okay. Now, this will wake you up if you're getting sleepy. Let's see. Do I want to do this? Yep, I do. I'll do it something like this. If this is our rigid body, with an axis of rotation that's perpendicular to the surface. Perpendicular to the surface. And we've got some point out here. So this is at right angles to the surface. And we've got some point out here on this body, maybe right there. At some distance, r. And there's a position vector that comes from this axis out to that. This body is in, let's say, by right-hand rule, it's rotating in this, around this axis. It's in rotation around this axis. Now, you can look at that image and think one direction or the other direction, depending on how you're looking at that arrow. So I always, the way I do this is I show double arrowheads for my omega and alpha by my right-hand rule. And so let's say we also put an alpha on there. Okay? So the thing is in rotation, and so this is a vector quantity, and so is alpha. Omega and alpha are vector quantities, and so is R. Now you know, based on what we just talked about, that that particle rotating about this axis that's perpendicular to the surface, you know that that is in circular motion on the plane of the surface. And it's moving tangentially back in that direction, isn't it? In the plane of the plate. Feel good? So, now some of you have had more advanced level physics, so you guys just keep quiet. But the rest of you that haven't, think about this. How can we use omega? We know that that speed's magnitude is r omega, right? We know that speed's magnitude is r omega because that angle down on the plane of the surface there is 90 degrees. So that speed's magnitude is r omega. What I want to do is I want to come up with that vector using this r vector and that omega. The r vector and the omega vector. So take your hand and think about cross products of which way do you have to do a cross product with your r and your omega to come up with a vector that points that direction. Think of upward as this axis. R goes outward, and your omega's up. Excuse me?
The omega cross R.
Omega cross R. The omega's upward, crossed with R, and that gives you the direction of that velocity, and the magnitude's built into it. That's going to be equal to omega cross R. What's in the same direction as that V?
Tangential.
The tangential acceleration. So the tangential acceleration, how are you going to get it as a vector?
Alpha cross R.
You know its magnitude is R alpha.
Multiply it by V hat.
Thank you. Okay.
Yeah.
Alpha cross R, right? R alpha times V hat. Yeah, that works too. Okay. Does that make sense? This is the direction we're going. You're going to be spending the rest of the term using these type of expressions. Let's see, what are we missing? Oh, this is a rigid plate. So there's an acceleration term that's coming back this way. Notice I put on AT, we hadn't done this at all previous in this term. We had not put an arrowhead, a vector arrow, on that particular term in the acceleration. That had been a scalar quantity. Now we've got it represented as a vector quantity. It's got the direction built into it through that cross product. Now, how are we going to get this guy right there? That normal acceleration. You know its magnitude, because it's circular motion and it's directed back towards this polar axis. You know its magnitude is r omega squared. So how are you going to get r's vector and omega's vector and come up with r omega squared's magnitude and pointing back towards the pole, or the axis? Time's up. Okay. Omega cross R. Joel knew it. Okay. Do I need parentheses?
It doesn't matter which one you cross.
What if you started by trying omega cross omega? Zero. So there's a forced order in the process here. You have to carry this out, and look at what that is. You know that is what?
Your velocity.
That's V. Look at it. Omega is upward. Cross that with V, and you get a vector that points right back towards the axis here. Okay? So that's a summary of the rotational motion concepts for rigid bodies. And I think we're just, you had a question? We got time for a quick question, I think. How much time do we have left back there? 5 minutes roughly? Okay. Okay. Yes.
I'm right-handed.
Okay. I think Daniel's pondering. Okay. So take omega and cross it into V, and your thumb will point back towards the axis. Take omega, crossed with V, and your thumb will point back towards the axis. Okay. So I think that does it for today. We'll start working problems with absolute motion and circular motion kind of things tomorrow. Okay. See ya. Yeah.